Hi, this is the second half of 6.8. This is the logistic growth model. And again, you might want to make your screen a full-size screen. And the formula on this one is P of t equals C divided by 1 plus A times E to the negative B t power. And where A, B, and C are constants, and A is greater than 0 and C is greater than 0. Now, this is actually a growth model, and it looks like this one is actually growing and it's getting leveling off at y equals c. And c is actually called, the c right here is actually called the carrying capacity when it's growing. So basically, this doesn't grow without bound. This actually grows to a certain point and then starts leveling off. And it's going to be a growth model when b is positive. Now that's kind of misleading in the formula because it's going to have a negative in front of the bt. And when that happens, it's going to be a negative number period and it's going to be actually growing because b is actually positive, but since there's a negative there, it's actually growing. So a decay rate with B is negative, and so it's called the decay rate. And like I said, for growth models, C is called the carrying capacity. So if you put like some kind of an animal on some islands, they start growing and start growing. Well, they're not going to grow without bound. There's a certain point that the capacity that the island can have is going to hit its limit. And that's what's going on right here. Now, on the decay logistic model, it's becoming extinct. There's a certain population, okay? The population is becoming less and less, and eventually it levels off to zero. That's what we call becoming extinct. So, and that's called the logistic decay model. And to be quite honest with you, we talk about this one probably more often than this one. I don't know why. It's just kind of one of those things. It's people give more examples using a logistic growth model as opposed to a logistic decay model. And I think both of them are just as important. It's just that's just what people choose most of the time. So, but anyway, I give an example and talk about environmentalists. And the environmentalists often capture endangered species and transport the species to a controlled environment where they can produce offspring and regenerate its population. Suppose that 6 bald eagles are transported to Montana and set free. Okay? Based on the experience, the environmentalists expect the population to grow according to the formula 500 over 1 plus 83.33 e to the negative 0.0162 times x. So this is our formula. So if you notice, A is actually going to be 83.33. C is going to be 500. And then B is actually 0.0162. I know there's a negative in front of it, but the 0.0162 is the B. Because remember, the formula has a negative B, which is kind of misleading a little bit. So they want to know what the carrying capacity is. So this state, wherever they put this, what region in Montana they put in, can carry 500 because that's what C stands for. It's the carrying capacity. So what is the carrying capacity? It's the top number. So what that means is we can't grow any more than 500 eagles in this area. Well, if it starts doing that, well, it can't. That's just in theory, it can. And so what they'll probably end up doing is once it reaches 500, they'll probably start scraping those eagles off and bring them somewhere else. So, but in this particular example, 500 eagles is what it can carry. Now, what is the growth rate? Remember, the growth rate is B, and so in this case, it's going to be 0.0162. So it looks like it's going to have a 1 point. Actually, I think I need the decimal right there if I remember the problem correctly. It's actually 0.162x, and so it's actually going to be 16.2%. Okay, so pretty sure that's what we have. Yes, and now, so that's going to be growing at a 16.2%. Now, what is the population in 3 years? So, well, what that basically means is I just need to put a 3 into the formula, and that'll tell me what the population is in 3 years. So it's just a simple plug and chug. So P of 3 would be 500 over 1 plus 83.33 e to the negative 0.162 times 3. All right, so I need my calculator for that, and see what I get. So it's 500 divided by parentheses 1 plus 83.33 times e raised to the negative 0.162 times 3. And we have, it says 9.56. So 9.56, now that's not quite 10. You're like, where do you round it up to 10? No, you're not quite there yet. So it's actually, everything needs to be rounded down. So there are actually 9 eagles, if my calculations are correct. So, and I think I got it, yeah. And then times it by 3, yes. So that's that's how many eagles there would be in this area that they put in. You remember they put in 6 to begin with. There were 6 bald eagles that they put in, so they grew by 3 eagles in that amount of time. Now they want to know, when will the population reach 300 eagles? So what you have to do at this point is not put 300 in for the time. We don't want to know how many what the population is going to be in 3 centuries. We want to know when the populations of the eagles are going to reach 300. So what you need to do is take 300 equals 500 over 1 plus 83.33 times e to the negative 0.162 times the time. So you have to solve for time here. And that's not too easy. That actually takes a few calculations and a few steps. So you're going to have to actually get rid of this fraction by getting this part and moving it to the other side. So we have 300 times 1 plus 83.33 e to the negative 0.162 times the time equals 500. Now you got a couple of choices. I like to do the easy way out, but you could distribute the 300 if you wanted to. I'm going to choose not to. I'm going to move the 300 over to the other side. So I get 1 plus 83.33 e to the negative 0.162 times the t. And it'd be 500 over 300, which is 5/3. And then I'm going to subtract this 1 on over. You're like, what are you doing? Well, I'm trying to get this exponential by itself. So then I can take the natural log of both sides. So I can bring the t down. So it's a slow process. The process is just trying to skim things over to the other side as much as I can. So I'm going to take 1 over here and put it over here. So I get 83.33 e to the negative 0.162 t. And I move 1 over here, and that's going to be 2/3. Okay. So then I'm going to divide by 83.33. So that's going to be a little bit of a mess. So it's going to be e to the negative 0.162 t equals 2/3 divided by 83.33. And no, I'm not going to break down and use my calculator, at least quite yet. I'm going to leave it as it is, and I'm just going to keep putting that little lump in there. And I'll put it in my calculator all at once. So I take the natural log of both sides, and it turns out that t is equals to the natural log of 2/3 divided by 83.33 divided by negative 0.162. Few steps I'm probably leaving out there for you, but I think you go from here to here, I think you'll figure it out. Okay, so now you get your trusty calculator out. So you get natural log. Okay, and then I'm going to take parentheses again, 2 divided by 3, close the first parentheses off, divide that by 83.33, close that parentheses off, and then divide that quantity by negative 0.162. And I get 29.8. So 29.8 years. So almost 3 decades. It takes almost 3 decades in order for your eagle population to go from just 6 to 300. So it does take a while for this population to regenerate itself. And so, I mean, you got to remember now, eventually it will get up to 500, or close to it. It won't get quite to 500, but it just stays under 500. So, but 500 is the carrying capacity, and 300 is definitely in there. So, yeah, well, what happens what if you try to make this 600? What would happen? When you try to solve this equation, you'll be end up taking a natural log of a negative number, and you'll get an error, and because you've exceeded your carrying capacity. So if you try to make this number bigger than your 500, then you're going to have a problem with your calculations over here. So you'll know you made a mistake if you try to do that. It won't give you an answer. It'll just say domain error on that. So, but anyway, this is the second half of 6.8, and there is another example with the logistic decay model. The problems are pretty much the same thing, except they're going to be asking for less than what you started with, but it's still the same concept. So, and they might want to know, how long will it take to half of what you started with, because it's going down. So, but anyway, that's the idea. So that is 6.8.